Can you hear me? Yeah. Okay. So also the topics we're going to discuss now is basically just a review of a particular case, or a generalized case of that was discussed in Joseph's lecture. Hopefully the point of view is slightly different. And as Joseph said, so we had little decompositions yesterday. And now the idea is to decompose the measure into Gaussian localized pieces. Yes, so he said that. So you multiply the original density by some Gaussian factor, and the average of these factors gives you back the original measure, so they are no longer disjoint. Earlier, it was a disjoint decomposition into things with disjoint support. Now the supports overlap. Okay, but it's still okay. Yeah, this is stochastic localization method. It was invented by Ronen Eldani in his PhD many years ago. We heard about it in great detail in Joseph's work, and we'll see us probably more this afternoon about the difficult stuff. But what I'm going to do is just a rather degenerate case of this method that we'll discuss. Okay, so we have, in particular, there will be no stochastic processes. So we have just Z, a standard Gaussian random vector in our N. And we'll have, bless you, and we'll have X, which will be a low concave random vector. Independent of Z, of course. And I think its low would be the measure mu, and the density would be the function rho. This is my usual notation. Okay. And now we're going to decompose rho. Okay. So we'll decompose rho into these Gaussian localized pieces. Decompose rho. Okay, where the rho is this. Okay, so this is our idea. And so Joseph had this parameter t and the parameter s, which was 1 over t, and they varied. It was a process. We don't vary the parameters. We just fix the number s to be fixed in this lecture. And we consider the random vector ys, which is the sum of x and a Gaussian of variance s. Okay, so you see the traces of some Brownian motion here. It's like, but no, for us s is fixed. We don't view it as a process. Just this random variable, it's a blurring of x by some Gaussian noise. That's how we think about this thing. Let's write, so if we write gamma s for the Gaussian density, of square root of sz, so the density of ys is the convolution. Okay. Now we have the following proposition, which is, I think, the simplest Gaussian localization. So for point y in Rn, we consider the Gaussian localized piece. Sometimes I call it Gaussian needle. That's a mistake because it's not the needle, no? But I cannot help it. Okay, Gaussian localized needle piece, which is the following function. So it's rho of sy, OYS of x. So we take rho of x, the original density, and we just multiply it by a Gaussian. That's it. Maybe put y minus x to look a bit nicer. Okay, so all we have our density. And we just take some point y. It is the center of a Gaussian. And we multiply by the Gaussian density. And we normalize. How do you normalize? This is by the convolution. So this is probability density. Okay, so this is Gaussian localized density. And the claim is that rho is a mixture of these things. Of rho is. Maybe rho sy, I think is better. Because later I'll just erase the y, so the s would remain. Okay, a mixture of rho s as follows. So rho is just the expectation of rho of s with ys. Okay? Or if you want, so for any x, rho of x is the expectation of rho of sys at the point x. Okay, just this is in brackets. This is just, so this is our decomposition. These localized pieces, they combine together to give us the original measure. Okay, so this cannot have a complicated proof, of course. This is basically just the law of total probability or something. So let's see. So the joint density of x and ys, what is it? So ys is x plus root of sz. Okay, so yeah, we have this, we think of Rn and Rn. Here we imagine x, and here we imagine ys. And the density is like that, so it's rho of x. Right, so the first quantity is just rho of x, and the second one is a Gaussian centered at x. So it's gamma s y minus x. This is the density of this pair of random variables, random vectors. Okay, so the conditional, what's now the conditional distribution of x? So these are smooth functions, or I don't know, continuous functions. It's not, you don't need fancy theory to do conditional probability. So the conditional distribution of x conditioned on, okay, my English is so-so, but so conditioned on ys equals y is what? So you look, suppose this is the point y. I look at this, the restriction of the density to this subspace. It is this function, but I want to normalize to get a probability distribution. So I divide by the convolution, so I get rho of sy of x. Okay, so this is rho of sy is the conditional distribution of x, conditional on y equals y. And now we just use, I mean, the total probability, the law of total probability. How is it called? Finishes the thing. So okay, let me do it. Yields the proposition. Completes the proof, but let me explain. So if I take any test function f of two variables, x, y, I can say that the integral of f x, y with respect to this law. I just write it as double integral. First of all, the integral of fxy with respect to this measure rho sy dx, and then here I put back the convolution. And now if f depends only on x, what I would get is that, so this integral over y, this is dx dy, the integral over y will be 1, and giving nothing, so I get the integral of f times rho would be the integral over Rn. Here I'm going to have rho gamma s y dy. And inside, I'm going to have the integral of Rn of f rho sy. Or if you want, this is the, so this is the density of ys. Okay. Okay, so this is the expectation of the integral over Rn of f rho sy ys. Okay, so this is why this decomposition, and I denote, I abbreviate usually or sometimes. I erase the y. So rho of S is rho of S at this random ys. So rho of S, this is a random density. Okay, so we have this decomposition. Okay, what are the properties? Why do we like it? So it has two properties, two good things. The first thing is that rho S, I say, is more or less concave than gamma S. But in the notations that we used in the previous hour and yesterday, or this means that rho S is 1 over S uniformly, this is true? Uniformly low concave. Okay, so, but it's, at least for me, it's easy to think that there is gamma S, and this is just more low concave. It's like this. That's the way it's smaller than gamma S in any respect. Okay, that's one property. And the other property is somewhat heuristic or intuitively, heuristically, or intuitively. So there are two regimes. The critical value for S is the Poincaré constant. And if S is larger than Poincaré constant, then the random measure, the density rho S, which is a random density. So what do? We multiply the measure mu by a density which is kind of almost one, almost constant, because we take a Gaussian of large variance. So it's like constant function almost. You multiply. So then density rho S is somewhat similar to the original measure rho. So nothing changes. It's like rho. And for S, which is much smaller, it's the other way around. So we multiply by a small Gaussian, so the localized pieces are very small. So the localized, the really localized is small, almost like a delta measure, if you want. This is a bit exaggeration, not really a delta measure, but at least if you want something to remember, it's a very small thing for S, which is small. This is the two main properties that we have to think with this decomposition. So it's somewhat of different character. So we had needle decomposition, something very specific. You construct it, you have many kinds of needle decompositions. For any function, you can construct some things that the average will be 0 on each, something very, very sophisticated. While here we have something, if there is just one parameter S, it gives a decomposition, and and we're going to work with this. Okay, questions? Always there are questions, no? Okay, but next time when I prepare a question for the next time, okay? So it won't be like, should be questions. Okay, so let me continue. So we consider the conditional distribution, conditional expectation operator. Which was in Joseph's lecture QS. So QS for a function f. F is a function on Rn. So the value of the point y is simply the integral of f times rho s y. Or if you want, actually the more, let's write this way. It's nice to write it using conditional expectation operator. So QS at ys, okay, is the expectation of f of x conditional on ys. So this is the operators. And now let's note that we can, that for any function f, we can decompose the variance. The variance of f of x. So what that means is, I think it's called the law of total variance. Not sure. So it's the sum of the variance of f of x conditional on ys of the variance of the variance on ys of the expectation of f of x, condition on ys, plus the expectation on ys of the variance of the expectation of the variance of f of x, condition on ys. So that's the variance with respect to the conditional measure of x and the expectation over ys. Okay, so this is the law of total variance. Variance of the expectation plus expectation of the variance. Okay, and let's write it a bit more in our notation. So this is what? This is the variance of qs of f at ys. And this thing is the expectation of what's the variance of f of x condition on ys. The distribution of x condition on ys is just rho s. So we have the variance with respect to rho s of f. Okay, variance, let me remind you, integral of f squared minus integral of f rho s squared. Okay, so these are no variables. Okay, so the variance is sum of two terms, qs and the variance with respect to rho s. And the question is which of these terms is dominant. And now if s is large, I said that rho s should be roughly like rho. So you might say that, I mean, this should be the dominant term. And this is indeed correct. Okay, so for s which is larger than Cp mu, the second term is indeed dominant. Second summand is dominant. And we have the following lemma. So for any f in L2 mu, I mean just integrable, so integrable. So if I look at the variance, the variance with respect to the homogeneous measure rho of f, so we know it's at least the second term because the sum of them is the variance. And the claim is that it's not much larger. So if we denote by alpha the ratio of s to the Poincaré constant, okay, so think of, we only work with alpha which is at least 1. Then I think what I prove is at least 2 plus 1 over alpha times the expectation of the variance of rho of s. Okay, so the claim is that, I mean, the variance is pretty much this term because when you localize, you didn't change much if s is large. It actually could be 1, yeah. Okay, remark, yeah, good. Okay, let me say. I know to get 1 if you want. You know, it's like I feel guilty for putting. Yeah, you're right. But of course, I answer to a different question because I feel guilty to writing the 2 because I know to prove 1. Okay. But it's, I mean, for us, it won't be useful at all to prove. But okay, let me just write a comment and then prove it. Wow. Okay. So let me just write the lemma again. So the lemma was that alpha was s over Cp mu, and what we claim was that the variance at the second one, right? This makes sense. So this is at most 2 plus 1 over alpha times the expectation of the variance for s of f. Okay, and just a comment. It's possible. So we can can improve in 2 ways. So we can change it to 1. This is first thing we can improve. And second, no locality is not needed actually. So it's true in great generality. But for this to prove this one, you need to differentiate with respect to s. To let s vary in differential request, which I don't do. I take x fixed. This is Joseph, he differentiates this. So, okay. But this will be enough for us. Okay, any questions before I prove the lemma?
Yeah,
No. Can I give you a sneak peek for 1 second? If you, no? Won't you? Okay. 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 So this was the lemma. This was just copy the lemmas that I'm going to put. Okay. Okay. Also the notes. There are notes with everything. Okay. All right. So let's use first of all the subadditivity of the Poincaré constant. So ys was x plus root of sc. So it's at most this plus, well, combination of root of sc, which is just s. Okay, very good. Now, in the law of, okay, I need to copy things from the board. Okay, so just recall that the variance was sum of two things. Okay, I use it here. So this was the sum of two things. This was the sum of variance with respect to rho s plus the variance of qs f of ys. Okay, so this is a useful formula. So we want to show that this is dominant, so we want to show that this is small. Okay? How do you show that the variance of a function is small? You need some cancellation, and the Poincaré inequality comes to your help. So by Poincaré, the variance of qs of f of ys is at most the Poincaré constant, which I just computed, times the L to no of the gradient of qs of f. Okay? So I will use it later, because first I need to compute what this thing is, right? What is the gradient of, we don't know. It's some formula. Okay. So let's compute the gradient of QSF. Okay, so QS of f, let me remind you, is rho x gamma s y minus x over the convolution. No, dx. I could put the rho here, but I did not. Okay. So right, this was rho sy of x. Okay. Now we want to differentiate this with respect to y. Okay. So many things do not depend on y. Rho and f do not depend, but these two things do depend on y. So we need to differentiate a Gaussian. And now for a Gaussian, so if you gradient of gamma s of some point x is minus x over s times gamma s. If you look at the logarithm of gamma s, it's minus x over 2s. So that's what, this is the differential. And therefore, gradient of qs of f at y is going to be what? So everything is like logarithmic derivative. So I put here rho s of y x f of x dx. Actually, well, okay. And here, what should put? So if I differentiate the thing here upstairs, I'm going to get x minus y over s. But here, and if I differentiate this thing, I don't know what I'll get. I get some function of y. Of y. Okay, and s. S is fixed, but okay, of y and s. So that's what I'm going to get when I differentiate these things. In fact, I may erase this y here because it can be absorbed there. It's better to put it this way. X over s plus something depending on y and s. And how would I determine this function of y and s? So if f is just a function 1, we know that grad qsf vanishes. Qs is also 1, so this equals 0. Okay, so you know that this is a function of y such that the integral of x over s with respect to this measure is 0. So this must be the barycenter. Okay, so if we denote by AS, or AS of y, the barycenter of rho sy, we get that grad QS at y is the integral of x minus AS, or AS over S, f of x, rho sy. Okay, so we need to do upper bound on of grad QS. Okay, so grad QS. So let's so for any theta, if I look at grad QS f of y, just pointwise bound for the gradient. So this is the integral of x minus as. Let's move to 1 over s outside better. So x minus as theta times f of x rho sy x dx. And I do the same Cauchy-Schwarz that I did, I mean, like 3 times already, maybe. So this has integral 0. So this is at most 1 over s outside. So this is the covariance of rho s. Let me erase the y. It's too heavy notation. Covariance of rho s theta times theta times the variance of f with respect to rho s. Yes, okay. And therefore, I was very smart to put a star in the Poincaré inequality over there. Okay, so we get that grad QS, this is for any theta, so grad f s of y square is at most. So I'm going to get 1 over s square times the variance with respect to rho s of f at y times the operator norm, let's say, of the covariance of rho s. Okay, but let us use low concavity, we are allowed. So the density rho s is more low concave than gamma s, right? It's more peaked, if you want. It's more, it's smaller than gamma s. And this implies that the Poincaré constant of rho s is at most s. So in particular, the covariance of rho s is also at most s. So this thing is smaller than s. So in total, we get 1 over s, the variance of rho s y f. Okay? And therefore, by this Poincaré inequality, so the variance of QS of f of ys is at most what? So it was 1 over s times this thing times the Poincaré constant, which was here. Okay, so this is 1 plus what you want. And we will get 2 because we'll say that the variance of f of x is the sum of 2 things, and the second, so it's computation of the variance for s of f plus the variance of qs f of ys. So it is at most, so we don't touch this thing. This is 1. And for the other thing, we go to the, so it's 1 plus s over the cpx over s. Okay. But really, we don't care about this factor 2, so it's okay. Okay. So this proves this lemma. Okay, questions about this lemma? Okay, so the conclusion was that if s is larger, let's see. Okay, so let me just repeat. So if s is larger than Cp of mu, then we know that the variance with respect to rho of f, then for any f, is at most the expectation of the variance with respect to the localized pieces. Okay, now we are going to have two corollaries for this lemma. The first corollary is that, again, alpha is S over Cp of mu. And the claim is that the Poincaré constant of mu, of rho, let's put, is at most 1 plus 1 over alpha times the Poincaré constant of the localized piece. So we said that for large S, if S is large, so alpha this thing is bounded by a constant, rho S should be roughly like rho. So it should also have some kind of the same Poincaré constant, and in expectation, it indeed does not go down at least. Okay, so let's prove it from the lemma. So let's use this improved reverse figure by Emmanuel Millman. There exists some one-Lipschitz function f. It's obviously in L2 of mu, because it's one-Lipschitz, but okay. And we know that it's, Joseph discussed it a lot, we know that this one-Lipschitz function is such that its variance is at least, let's say mu, is at least the Poincaré constant. Okay? Therefore, okay. You want this one up. So I should, I could have arranged that, yeah, okay. Maybe in my last lecture tomorrow I would be good enough to understand how to finally do these boards reasonably well. Okay. Okay, so we know that the variance, what we said is that F1 Lipschitz, and the variance of F is pretty large. On the other hand, by the lemma, we know that the variance of F was at most 2 plus 1 over alpha. The variance of F with respect to rho S. So let's apply Poincaré for rho S. So this is at most 2 plus 1 over alpha, the expectation of the Poincaré constant of rho S times the integral of grad F square. So it's convenient to assume it's one Lipschitz, because then you can just move at most 1. So we got at most 2 plus 1 over alpha, the expectation of the Poincaré constant. Okay, and we recall that this is at least 1 over C. Okay, this is at least C times the Poincaré constant of U. So this proves this corollary. Okay, so we know that the Poincaré constant do not change. And now let's just, any questions here?
Yes.
Please.
So the problem you had, you use Emmanuel's result because you don't control the centering,
Yes.
the centering of F, essentially.
Not quite. So I could do other things. First of all, it's not like a tool which is you cannot avoid completely.
If F was always centered with respect to rho S, you could just...
No, the centering was done in the lemma. Centering is not, the centering was done before. So for any F, I have the variance of rho S of F. It's always, the centering of F is okay. I dealt with it already. Now the issue is that if I apply Poincaré, L2 Poincaré, if I apply, I get integral of grad F square. So you could do some Cauchy-Schwarz, for instance, and say, okay, you know, the L2 norm of these things gives you back the, but I prefer to do it this way to get 1. It's a bit. So that's the issue. So, otherwise, I'd have to do some further manipulation for the grant. But probably. Not, I didn't completely check, but probably. I have some, yeah, okay. More questions?
So Cp is also on the other side, in alpha. Is it?
Cp?
Alpha is...
What?
Alpha is equal to...
Sorry. Alpha is just the ratio of S over Cp of mu. So if,
So you have CP on both sides.
but this is mu and this is rho s.
Yeah, yeah. Alpha.
So this gives you, let me, Cp of mu is at most 1 over c times 2 plus 1 over alpha times the expectation. And this thing for me is big C times 1 plus 1 over alpha. That's what I... No? Well, what? Well. What?
I think people want you to solve for CP or something.
Is there an issue? No. Okay, okay. Now, but it did not break. Okay, now let's use the fact that we enjoy so much that rho s is more or less concave than gamma s. Okay? So you know that, let me now say it in the terminology of yesterday. So rho s is 1 over s uniformly log concave. It's very nice because we can use the improved Simonovits. So Cp of rho s is at most root of s times the covariance of rho s. So the corollary now is that, corollary number 2 maybe, is that Cp of mu is smaller than some, okay, constant times 1 plus 1. I mean, this will be really, let's say, assume, okay, alpha is not, it never appears, times root of s times the expectation of the covariance of rho s, the operator now. Okay, so whatever remains to be done is to estimate the covariance of rho s. This is a difficult task, but Joseph kindly agreed to carry it in this afternoon, I think, or maybe tomorrow afternoon. Okay, so what we can do now is just rely on his result. This will be not yet proven, but just see what will be the conclusions. So let's denote by S naught. So we know that, okay, so if you take, let me just note that what happens, so let's denote by AS the covariance of rho s. And just note that when s goes to infinity, I almost surely this would be the covariance of the measure mu, okay? Because we kind of multiply by things which are almost 1. You can, okay, this could be proved that basically we know how AS looks for very, very large S. Okay? So it makes sense to change, and let's assume that mu is isotropic now, so that the covariance is identity. And the idea that the difficult work would be to do the following thing. You reparameterize time, because you want to focus at infinity. At time in s equals infinity, you know that this is identity. And then you want to show it does not deteriorate that much when time progresses. So for that, you need to differentiate, get third derivatives and third tensor, etc. But we'll just use it. It's very convenient for me just to use it without working at all. So yeah, I should. So the analysis of the covariance process, I'll just quote. So a deep theorem, which is for done, and many people contributed to this success. Chen the breakthrough a few years ago. I think also Joseph could be blamed a bit. Okay, and this is user characterization, and the claim is the following. So let's denote by S0 to be, so for large S, we know that the operator norm of AS is under control. So I want the minimal S for which is smaller than 10. Okay? Then I think there are several bounds for this. Each of them suffices for the best known bound on KLS. The first bound is that S0 is at most constant times log n times the supremum of Cp mu over all possible log concave random vectors. Maybe X, Y, Z, Y, R, W, where W is isotropic log concave in Rn. So this was known a few years ago. And using the the improved Simonovits, you can prove directly that, one of them is that S0 is at most log square n. And actually, this is tight. So at least the first estimate, in the case of exponentials, it's a tight estimate, it cannot be improved. And the log, so that's, why do we see the log? Let me just quickly tell you. So, I mean, if I look at the expectation, if for any S which is larger than the Poincaré constant, this is roughly identity. Because, why? Because the AS theta theta, right, this is the variance of, it is the expectation of the variance of rho S of x times theta, which is roughly, as we know, the variance with respect to rho of x times theta, which is 1. So we know that on average, AS is roughly identity, but operator norm, you need to control the maximal eigenvalue. And if, for example, you have the coordinates are independent, then you have the matrix would look like a diagonal matrix. On average, if the term is okay, with some tail, I don't know, exponential, Gaussian tail, but the maximum of these random variables would give you a log. So at least in some cases, there is no way to avoid this log, and nothing to do with this right now. Okay, but yeah, Joseph will talk about this a lot. So I'll just conveniently use it. And says that this gives a good bound. So corollary. So the currently current bound on KLS. So for any isotropic log concave random vector x in Rn, well, we lose the logarithm. This is the problem, we lose the logarithm. Okay, let's prove it. So this is corollary 2. So if you use, use corollary 2, which is just above me, I hope. Yeah, so corollary 2 with S0. So we know that, so if you use the second one, this means that alpha would be log square n, I think. So you get just that Poincaré constant at most root constant times root of s times 10, which is log n. Or if you use the first one with alpha, which is log n, so you don't log n times. Okay, if you use the first one, take x, which is worst possible with large Poincaré constant, the largest possible, or maybe up to factor 2, and then you'd get with this thing, you'd get that Cp of x is at most, so log n times Cp of x, which indeed again implies this bound. Okay, so I wanted to prove also Braskamp-Lieb today, but I guess I have no time, so any questions? Please.
Why is alpha such in this case?
Alpha is S over, in the first one, no, I'm not saying it.
In the second, which you...
In the second? The second, so I take S, this is S0. In the second. The second, it's not true, right? The second, I would say the following thing. So if the Poincaré constant is smaller than log n, I have nothing to prove. So all I claim here is that alpha is at least 1, let's say. So I take log square n, okay? So if alpha is, in this case, log square n over the Poincaré constant of x, okay? So I claim that alpha is at least 1. Because if no, at least 1, because okay, at least what I can see from here is that okay, if this is for the second proof, yes. If I want to have that alpha is at most 1, so I want to know that alpha at least 1, so I want the Poincaré constant to be at least log square. So it is. So I have to use that. Okay, so only this proofs works. That's what you seem to claim. So that one seems to be perfectly fine. But the first one, indeed, I didn't. Okay, so we prefer this proof. So this is what is written in the paper, in the notes. So we prefer that one because I was not careful with the alpha to apply the second estimate. No, but it should be okay. It should be okay. It should be okay also with the second one. I mean, yeah. So you think that this is too small, but wait, no, wait. Yeah, right. Yeah. This is fine. Also with the second proof, because.
You use the other bound for CP, like the easy one. No.
So the thing that I claim is that, okay, let me do the following thing. So if, so what we get is that if CP of x, say, is in the range log n to log square n, right, this implies that CPX is smaller than log n. Okay, so this is what you, I mean, this is one way. Suppose that CP of x is in this range, between log n and log square n. So it means that with this alpha would be at least 1. Okay, so you'd get that CP is at most log n. So there are no Poincaré constants in this interval, in Rn. But there are things which are 1. So you can interpolate x plus the Gaussian. The Gaussian gives you 1. You can never enter this interval. So you must be at most log n. That's a clumsy way to recover this argument. And it should work directly also. Okay, good. So, but at least things work. So more questions? Yeah, right. More questions? So the two proofs seems to be okay, and yeah, we continue at 1:45.